talking about equilibrium positions and Q's and K's and where things lie and all that kind of stuff. But we have what's called Le Chatelier's principle to help us to understand where the position is and how you can change to reduce the stress caused by something. So, for example, when manufacturing a chemical, when chemists and chemical engineers want to have as much product created as possible for a reaction. So they want to make sure that they want the equilibrium to lie far to the right, meaning that you'll make more products at the end when it reaches equilibrium. So we qualitatively predict the effects of changes by using what's called Le Chatelier's principle. This tells us that if a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that will tend to reduce that change. So you can predict lots of things with Le Chatelier's principle. Some of these stresses that will have effects include changes in concentration or pressure and volume, temperature. That's what we're going to focus mostly on right now. Later on we can talk about pH and colors of the solution. So concentration, meaning that if you have a reactant product that's added or taken away from the system at equilibrium at constant temperature and pressure or constant temperature and volume, then the equilibrium position will shift in the direction that lowers the concentration of that component. So if you're adding something to it, you want to lower the concentration. If the component's removed, you want to raise the concentration. That's a lot of words. More simply, if you add something, you shift away from it. So for example, if you add a product, you would shift towards the reactant. So your answer would be shift left. If you remove something, then you want to shift toward what you removed to make up for what you took out of there. So if you are removing a reactant, that will shift left so that you can create more of that reactant. Or if a product is removed, then you would shift towards the products. So this add, shift away, remove, shift towards idea is the simplest form, and if you can get that down, you can nail almost all of this. Okay? Everything applies to that add, shift away, remove, shift towards. So let's see what happens with this reaction and how it will respond to the following changes. So the first one is the addition of carbon monoxide. Well, carbon monoxide is a product, so that means that we're going to be adding a product. And if you add something, you shift away from it. So we want to shift away from the product side. So the answer will be that you shift left. Some people just put a left arrow. Either way, so that what that means is we will shift to use up that extra carbon monoxide and create more of our two reactants. Okay, B, we're adding carbon, which is a reactant. So this time we're adding a reactant. So we want to shift away from the reactants. So the answer will be that to relieve the stress, it will shift to the right. You can draw your arrow. So that it uses up that extra until we're back at equilibrium. Okay, and C, we're removing AS4. AS4 is a product, so we're taking out some of the product from the system. And if we're taking some of that product out, we have to make more of it to go back to equilibrium. So the answer for C is that it will shift right. So remove, shift towards, add, shift away. This is how that all works. Now let's talk about pressure changes. So this only really affects when you have gaseous components. Okay, so you can add or remove a gaseous reactant or product just like we just did. You can add an inert gas, which is not involved in the reaction, but it may change the pressure. And you can change the volume of the container. So all these three ways are how we affect pressure. So adding the inert gas, the gas is not involved in the reaction, will increase the total pressure of the overall system, but it does not have any effect on the concentrations or partial pressures at equilibrium. So that means that the system will remain at the original equilibrium. So another way to say that is that there is no shift when you add an inert gas. When the volume of the container holding gaseous system is reduced, then the system will respond by reducing its own volume. So this is done by decreasing the total number of gaseous molecules, so you shift to the side with less. Or if you want to increase the volume, you shift to the side with more. It's important to know that volume, or just remember that volume and pressure are inversely proportional. Okay? So if you want to decrease the total number of gaseous particles, so you're decreasing the volume, so I'm going to say down for volume, then that means that you shift to the side with less gas molecules. Okay? And if you wanted to increase the volume, then you would shift to the side with more. And then, so just know that that is opposite for pressure. So, because pressure and volume are inversely proportional, so if you reduce the volume, the system will shift to the side with less to reduce its own volume. If you increase the volume, you shift to the side with more. So for pressure, if you need that in pressure terms, if you want to, it's opposite. So if you are decreasing volume, that means you're increasing pressure, you shift to the side with less gas. And if you're decreasing the pressure, you shift to the side with more. Okay, it takes some thought for pressure and volume. And how does temperature change it? The previous two changes don't affect the value of K, but temperature does. That's why in every single problem it will say at this temperature or at a certain temperature, because K is dependent on temperature. So the addition or removal of energy by changing the temperature will affect K. And how it affects it? You want to treat the energy as a reactant or as a product. So we know reactants means that you're gaining energy, so that would be an endothermic process. And exothermic is when you're releasing energy, so that would be considered a product. So then once you know that the reactant or the product is where you put the energy, then you can just use the same rules of adding, shift away, and remove, shift towards to figure out the change of the temperature and the shift. And then if you are to think about how does this affect K, because I think that's what example 11 asks us, when you are shifting to the right, that means that you are going to increase the products, so that means that the K will increase. And if you shift to the left, that means you're increasing the reactants, and so then the K goes down. And it all has to do, so decrease for K, it all has to do with how that ratio is set up for your equilibrium expression of products over reactants. So if you're shifting to the right, you're producing more products, so your numerator gets bigger, and that's why K increases. And if you shift left, the denominator gets bigger, so then the value of K is lower. So for each of these reactions, we want to predict how the value of K changes as the temperature is increased. Okay? We have an endothermic reaction and an exothermic reaction, so you can see both options. So the first one is endothermic because the enthalpy is positive. So that means that I'm going to treat heat as a reactant. So just so that we can see it with this first one, I'm going to just write heat, but that is symbolizing that 181 kilojoules to be on the reactant side. Okay, so if we're increasing the temperature, that means we are increasing on the side where the heat is. So we're adding to the reactant side. So if we add, we shift away. So that means that the shift will be to the right because the heat is on the reactant side. And we just said when we shift right, then the K will increase. Okay, now for the exothermic reaction, negative 198 kilojoules released from this reaction, then we are treating the heat as a product. And this time we're still increasing the temperature, so we're still adding heat on the product side. So we're this time going to shift left because the heat is on the product side and we're adding it there. And since we're shifting left, then what happens to K? It decreases. Okay, so Le Chatelier's principle just helps us to predict the shifts. And when you shift something, that means that it's going to produce in the other way until it reaches equilibrium and can steady out again.